Hello class, welcome to part 2 of design of brakes. And in the first part of the design of brakes, we have seen the meaning and functions of a brake, the energy absorbed by a brake, heat dissipated during braking, and some of the characteristics that the brake lining materials should have, and also the material properties of the brake lining materials. Now in this lecture we will have the design of two types of brakes which have been mentioned in the syllabus of VTU. And before that let us once again go through the meaning of the brake and its function. Now a brake is a device by means of which artificial frictional resistance is applied to a moving machine member in order to retard or stop the motion of a machine. So if any moving member is there, so we have to apply some force in order to retard its motion. And there should be some elements involved in it, and our purpose is to design those elements. Right. So another definition of brake is it is a mechanical device which stalls the motion. Now in a brake system, the kinetic energy of the vehicle is absorbed mechanically or electrically in order to decrease its speed. So the moving body possesses some amount of energy, and when it is being stopped by a braking system, the energy has to be absorbed by some means, maybe mechanically or electrically. In case of mechanical brakes, friction force will be there which converts the kinetic energy into heat, and in electric brakes an electric current forces a magnet to apply the brakes, bringing the motion of a moving body to halt or decrease its speed. Now again we will have a relook at the classification of the brakes. Broadly we have hydraulic, electrical and mechanical. And in mechanical we have radial and axial. In radial type of brakes, the force applied is in the radial direction of the wheel, and here in the axial the force applied to brake is along the axis of the rotating member. And in this radial type of mechanical brakes we have block or shoe brake and band brake. So these two we will be discussing as far as the syllabus is concerned. Now, let us go through the procedure of determining the braking torque. So main thing in the design of block brake or shoe brake is to determine the braking torque. Now as you can see in this figure, there is a wheel also called as drum, and this member is block or shoe which is mounted radially, and this is the lever which is pivoted at this point O. Now in this case the wheel is rotating in the clockwise direction. R is the radius of this wheel or drum, and 2 theta is the angle subtended by this block at the center of the drum, and P is the force applied at the end of the lever for stopping the motion of the wheel. As I mentioned, this lever is pivoted at this point. Now similarly this is the case where this wheel or the drum is rotating in the counterclockwise direction. Now let us have look at the notations used in these two figures. P is the force applied at the end of the lever here. So this force will be utilized to apply the brake, means in order to decrease the speed of this wheel or stop the motion of this wheel. Rn is here the normal force pressing the brake block on the wheel or drum. R is the radius of the wheel, this one. 2 theta is angle of contact surface of the block. So this is entire thing is block, and this block subtends an angle of 2 theta at the center here. Mu is the coefficient of friction between the drum and the block material. Ft is the tangential braking force, this one here. Ft is the tangential braking force or the frictional force acting at the contact surface of the block and the wheel. So at this point of contact between the block and the wheel, there acts the tangential force Ft. For clockwise motion, it is the direction, and for the counterclockwise motion, this is the direction. Now, we know that the magnitude of the tangential force Ft is given by the coefficient of friction times the normal force Rn, and this point is to be noted. If the angle of contact is less than 60 degree, that is 2 theta is less than 60 degree, then it may be assumed that the normal pressure between the block and the wheel is uniform. In such cases, the tangential braking force on the wheel is given by mu times Rn, and the braking torque denoted by Tb is Ft into R, where R is the radius of the wheel or the drum. So substituting for Ft, you get mu into Rn into R. Now let us have a look at the case number 1, where the line of action of tangential braking force, that is Ft, passes through the fulcrum point O of the lever, and the brake wheel rotates in the clockwise direction. Meaning, when this tangential force Ft, or the line of action of this tangential force, passes through this fulcrum point, that is case number 1. In that case, what will be the braking torque Tb, and when the wheel rotates in the clockwise direction. Now, for the equilibrium of this system, if you take the moment of all the forces about this fulcrum point O, then we have Rn into x, x is this distance and L is distance, equal to P into L, hence Rn equal to P into L by x. Therefore, braking torque is given by mu into Rn into R. R is this radius, and Rn is P into L by x. So in this case, for this particular case where the line of action of Ft is passing through the fulcrum point O, and when the wheel is rotating in the clockwise direction, the magnitude of the braking torque is mu into P into L into R by x. So x and L are these lengths from the pivot point. Now similarly, when the line of action of Ft is passing through this point, but the wheel is rotating in the counterclockwise direction. So in that case, this is the magnitude of the braking torque, and it is similar to the previous one. Same. So whether it is rotating in the counterclockwise direction or clockwise direction, when the direction of the tangential force Ft passes through this fulcrum point, then the magnitude of the braking torque in both the cases is same. Another important point to be noted is when 2 theta is greater than 60 degree, we need to calculate the equivalent coefficient of friction denoted by mu dash, and it is given by this equation. And when it is less than 60 degree, this is not necessary to calculate. Case 2. What is case 2? When the line of action of the tangential braking force Ft passes through a distance a below the fulcrum point O. As you can see here, the line of action of tangential force Ft is passing at a distance a below the fulcrum point. So this is below the fulcrum point. Note it carefully. So other things remain same, and when it is rotating in the clockwise direction, so as usual, by taking the moment of all the forces about the fulcrum point O, we have Rn into x plus Ft into A equal to P into L. So hence the magnitude of the normal force Rn is P into L divided by x plus mu A, and the braking torque, magnitude of the braking torque for this case is mu into P into L into R divided by x plus mu A. Just compare this. It is only x here in case 1, but here in this case x plus mu A. Now similarly, when the wheel is rotating in the counterclockwise direction and line of FT is at a distance A below the fulcrum point, then in that case, again by following the same procedure, the magnitude of the braking torque TB is mu into P into L into R divided by x minus mu A. So you see here it is x plus mu A when the drum rotates in the clockwise direction, and it is x minus mu A when the drum rotates in the counterclockwise direction, and the line of action of the force Ft is below the fulcrum point and at the distance A. Please note these differences. And last case, the third case is when the line of action of tangential braking force Ft passes through a distance A above the fulcrum point. Now in this case, line of action of this tangential force Ft is above this point and is at a distance A. Let us see what is the magnitude of the braking torque Tb for this and when the drum rotates in the clockwise direction. Now by using the usual process, that is by taking the moments of all the forces above this point, we get Rn equal to P into L divided by x minus mu A. Hence, the braking torque for this case is mu into P into L into R divided by x minus mu A. Now similarly, for this case, when the direction, that is line of action of Ft is above the fulcrum point and at a distance A, the braking torque Tb is given by mu into P into L into R divided by x plus mu A. Just compare these two equations. Now one important thing here is, if this quantity x is less than or equal to mu A, this quantity, then P will be negative or equal to 0. So this means that no external force is needed to apply the brake, and hence the brake is self-blocking. So when this condition is satisfied, means x is less than or equal to mu A, then the brake is self-blocking brake. So you don't require any external force to apply the brake. So note this point. Now second type of brake that we have to discuss is a simple band brake, and we will determine the equation for the braking torque for this simple band brake. Now this is the wheel or the drum, rotating drum. Now in this case it is rotating in the clockwise direction, and R is the radius of the drum, and this is the band which is wound or put around this rotating drum, and one end of which is attached to this point O, and other end is connected to point B. So point B is the fulcrum point. Over this point the lever OBC operates, means the force is applied at this point and this lever moves about this point. So whenever this lever is moved, then the band is pulled against the rotating drum and the rotating drum will come to halt. Now let us have a look at the various notations used here. Let T1 be the tension in the tight side, this one of the band, T2 the tension on the slack side of the band, theta angle of lap or angle of contact or angle of embrace of the band on the drum. So this angle, the angle between point of contact here and here. So the angle between these two point of contact, M and N. Mu is the coefficient of friction between band and the drum. Between the band and the drum, mu is the coefficient of friction. Because of friction only, the drum will come to halt. R is the radius of the drum. T is the thickness of the band. So this is the band. Let its thickness be T. and RE, effective radius of the drum, which is given by R plus T by 2. Now we know very well that the limiting ratio of tensions in this case is given by T1 by T2 equal to E raised to mu theta, or it can be written as 2.3 log T1 by T2 equal to mu theta. Now the braking force on the drum is nothing but the difference between the tensions in the band, that is T1 minus T2, and hence the braking torque on the drum is given by TB equal to T1 minus T2, braking force times the radius. Now this is the case when the thickness of the band is neglected, so it is R only, and when the thickness of the band is taken into account, we have to use RE. RE is nothing but R plus half of the thickness. So this is the braking torque. Now if the permissible tensile stress is sigma T for the material of the band, and if it is known, then maximum tension in the band is given by T1, tension on the tight side, equal to sigma T into cross-sectional area of the band, W into T, width of the band and thickness of the band. The width of the band W should not exceed 150 mm for drum diameter D greater than 1 meter and 100 mm for drum diameter less than 1 meter. The band thickness T may also be obtained by using the empirical relation, that is T equal to 0.005 times D. And in this table, for brake of hand operated winches, that steel bands are made of different materials. Here for the steel band, the following sizes are used: width of the band and thickness of the band. Okay. Now that takes us to the end of the part 2, and in part 3 we will have a look at some of the problems on design of block brakes and design of band brakes. Thank you.